Okay, so first of all, thank you to the organizers for inviting me to this nice, series of conferences. Okay, I will talk about classification of surfaces via Mori theory, and I will treat the following arguments. I will start by talking about the cone of curves in general for a projective variety over C. Then I will talk about some fundamental results in dimension 2, so the case of surfaces, rationality lemma, base point free lemma, and boundedness of denominators. Then I will introduce the cone theorem and the extremal contraction theorem. And these are the cornerstone to prove the minimal model program in dimension 2. Okay, so let's start. I will work over the complex numbers. Okay, X projective variety. Okay, we say that two divisors, Cartier divisors, D prime are numerically equivalent if D C equal D prime C for every irreducible curve. Let me say that dim X is at least 2. Okay, and I will write D numerical equivalent to D prime. Perfect. The group of Cartier divisors modulo numerical equivalence will be denoted by N1 of X, sometimes called num in some texts. Okay, this is the group of Cartier divisors, small numerical equivalence, and then I will denote by N1 of X Q this group, and this one. Okay. Now we have an exponential sequence. We are over C. In the analytic category, there is this exponential sequence. This is X. This is exact to the level H0, so we can start from H1, analytic category, of course. Eh?
X is smooth.
Yeah, at the moment, let me take X smooth.
Sorry.
But you have this anyway. Sorry?
Also, the good C is one. Testing card, the testing cards on which we do.
No, all curves. All irreducible curves. Okay, H1, H0, H1, X, OX, H1, X, OX star, then H2, X, Z, and let me finish with this. Okay, by Hodge theory, this is a lattice inside this one. Okay, and so we have this complex torus, which is actually an abelian variety. No, this for surfaces. Okay. Peak 0 of x is this complex torus here, which is the quotient of this divided by this. Complex torus. Where is h1 x of x? Where? Which one? Ah, yeah, of course. Thank you very much. Okay. This is a complex torus of dimension, what is called the regularity of x. Okay. And we have this sequence. Well, this is peak 0 of x. This is the Picard group. And here we have divisors modulo linear equivalence. And here we have the Néron-Severi group. Divisors modulo algebraic equivalence. Okay. Again, by Hodge theory, this Néron-Severi of x is just the intersection between the second cohomology group with coefficient in z with the h11 part. So, in particular, this is a finitely generated abelian group because this is finitely generated. And by Matsusaka, we have a relation between num and Néron-Severi, namely the numerical, this one, okay, is just the quotient by the Néron-Severi by its torsion part. So this is torsion-free. It is just the quotient of the Néron-Severi by the torsion part of the Néron-Severi. Example. X and request surfaces. Then Kx is a two-torsion element in the Néron-Severi group. So in N1, this is 0 because it's two torsion. Okay. The equality of this, I mean, in this case, PG equal Q equals 0. So in this case, Néron-Severi is the same thing as the Picard group. Perfect. The rank of this group, so this group and this group have the same rank. This rank is called the Picard number of the variety. So let me, no. Okay, so this. Okay, so the rank of N1 rho of x defined as the rank of N1 of x over z is called the Picard number of x. Cone of curves so for instance, if you take Pn, the cone of curves is the picker rank is 1, and the group is generated by the hyperplane divisor. Okay, Convex curves. Again, we have a duality here. Let n1 of x, 1 now is an underscript, over z, be the group of 1 cycles on x modulo numerical equivalence. Okay, so this means that 2-1 cycles are numerical equivalent if they have the same intersection number with every divisor. Is the dual notion than before. Then we have an intersection pairing. Okay, you take a divisor, then you can intersect with a1 cycle, and you obtain an integer number. So you have D, C. By definition, this is non-degenerate. Because all this stuff is defined modulo numerical equivalence. Now, if you take about surfaces, remark, in the case of surfaces, complex surface, so the x is 2, this is the pairing induced by Poincare duality on H2. Namely, you have a Poincare duality from here to here. This because if you have a projective surfaces as a real manifold, the underlying real manifold is a 4-manifold, smooth form, real 4-manifold, and so you have this Poincare duality. This is, and this is no, this is non-degenerate. So, okay. Now, in the sequel, I will work in the context of n1 of xr. So let me write I will not write R anymore. When I write in this way, I will consider always the extension over the reals. Okay. Definition. Cone. What is a cone? For me, a cone is a subset of a real vector space of finite dimension which is closed by multiplication positive scalars. So let V be a real vector space of finite dimension a cone C in V is a subset such that 0 is inside C. Let me write C in this way. 0 is inside the cone, and the cone is closed by multiplication by positive scalars. So if V is an element of the cone, a lambda is an element which is non-negative in R, then lambda B is in the cone. A subcone C prime in C is called extremal you must have, okay, this is not convex. It's a non-convex cone with this definition. But we will consider just convex cone later. Okay, but maybe, no, this definition is not a cone. But the cone we will consider will be convex cones. Okay, a subcone C in C prime is called extremal if, whenever, okay, two elements are in the bigger cone and the sum of them is in C prime, this implies that both of them are in C prime. And the one-dimensional extremal subcone is called an extremal ray. So the picture is, Okay, let's stick with convex cone now. Assume that the cones are convex, just to avoid pathologies. Okay, so the situation is like this. You can imagine you have this cone here. And these are the extremal. So you have this convex cone here, and you have the extremal rays here. Okay. Here's. Well, and now we are ready to define one of the main characters of this story, which is the famous Mori cone. Okay, so take X projective variety. You can assume it's smooth for the moment. Okay, take n1 of x. Now, this is a finite dimensional vector space over R. This is the real vector space, so I can endow it with a norm. For instance, the usual Euclidean norm. This is not really important what norm you choose, because all the norms are equivalent in a finite dimensional R vector space. Endow it with the usual Euclidean norm. Okay, take n of x. This is the sum of ai ci, where finite sums, where ci in X is irreducible curve. Okay, curve. And these coefficients are non-negative. So, 0. This is a subset. This is a subset inside N1. And take the closure with respect to this norm. Okay? This is called the Mori cone of X. So you must take, this object is quite, you take finite combination of irreducible curves with non-negative coefficients, but you must also take the closure inside the vector space here with respect to the topology induced by the norm that we choose. This is important because later we will see some example where this is not closed. So in order to have a closed cone, you need to take the closure. There are some, we will see some examples. Okay, so this up. So just as notation, and I will give you a couple of examples now. Notation for every divisor, Cartier divisor, D, we set this is the set of classes in this vector space such that intersected with D give a non-negative number, and similarly for greater than 0, lesser or equal to 0, and less than 0. And the orthogonal of D is the set of classes such that D times X is 0. Finally, we write in this way. For me, this set is just the intersection of the closed cone of curves with this half space, with this half space. Okay? So this is an hyperplane inside in N1. And this is an half space, closed half space. Example 1. Assume the simplest situation, rho of X equal 1. Okay, for instance, X is Pn, or X is a hypersurface in Pn with n at least 4, or a very general surface in P3, or a very general abelian varieties. Abelian variety. Okay, by Lefschetz, okay, we know that Pn is clear. Upper surface in Pn with n at least 4 because of Lefschetz theorem, and this because we know that a very general abelian varieties are the Néron-Severi group generated by depolarization. Okay, in this case, there is not so much to say. Take an ample generator. This is projective, so it has an ample divisor. This divisor must be a generator. So take an ample generator for N1. Okay, I'm just saying that. Okay, I want to think of divisors, so let me. Okay. No. Yes, okay. Take a generator here. This is the cone of curves, so I want to stick to the case of surface, so let me consider if dmx equal 2. Just let me talk about surfaces. If dmx equal 2, let me identify n1 of x to n1 of x. So n1 of x as a basis consisting of an ample divisor then let me call h. So n1 of x is just this. The vector space is generated by h, and the cone of curves is given by r greater than 0 of h. So it's half line. And the closed cone is a closed half line. So the situation is this. This is n1. So maybe in this example, let me not talk about this. Okay.
So in the definition of NE, we have just greater, not greater.
Where?
NEX.
Yeah, but you are taking the closure now.
No, okay, here we are taking just greater than 0.
Yeah, and this one.
Okay.
And then when you take the closure of this is the closed.
I mean, not the closure of NE.
And is a combination of irreducible. Yeah, because you are also. Yeah, right. Because you are also adding 0 there. Yeah, okay. So it's just. Otherwise, yeah. This is always the point. Some texts consider the cone. They want to add the 0 inside the cone. Some texts do not add the 0 inside the cone. So with this definition, actually, you must put here. Yeah, okay. This is, otherwise there is not a 0 inside. You are right. Okay. Okay, you are right. With that definition, we must add. Right. Oh, sorry. So, okay. You are right. Because this is in the literature, there is some discrepancies. Some authors say that the cone is just something which is closed by multiplication with a positive scalar. Some other authors add the 0. So when you add the 0, of course, in this situation, you must add the 0 here. And so this is closed in this case. A very degenerate situation, but with that definition, you're right. You must put this. OK, let me give a less trivial example. Sorry? Where? Oh, yeah, of course. This 0. Thank you. example 2, take something slightly less trivial, P1 cross P1. Okay, so this is a quadric, we know. With Segre embedding, you have a quadric here. Let L1, L2 be the two rulings. Okay. The class carves into rulings. So, in this case, the Picard group is the same thing of N1. It is generated by this. Okay, so a R divisor, I mean, Q divisor, and then you take a divisor, is effective divisor on X if and only if it is of the form A1 L1 plus A2 L2 with A1 A2 greater or equal than 0. And so, in this case, the cone of curves is closed and is given by this set. So, if you draw a picture, here there is L1, here there is L2, so this is N1. In this picture, we see that in this case, the cone of curves is closed, this is the first quadrant. So the cone NE is itself closed, so it coincides with its closure NE bar, the Mori cone, and this is generated by these two closed half lines. We will come back to this later. Okay, let me recall now what ample means. Okay, a Cartier divisor X on a projective D on a projective variety X is called ample if let me some multiple, positive multiple, MD of it defines an embedding into projective space. It makes sense to talk about ample Q divisors in this. I mean, if X is singular, you can have some Q divisor which is not a Cartier divisor, but in that case, the definition of ample makes sense as well, of course. Now, there is a criterion, famous criterion for ampleness, which is called Nakaimo-Ishii. There are several characterizations of ampleness, but I will talk about Nakaimo-Ishii and Kleiman's characterization because they are the numerical ones. They are in terms of intersections. D in X is ample if and only if we have that for every subvariety y in X 1s that you can, okay, you can find the intersection D to the dim X y times y, and this must be positive. And you must test with all subvarieties, and if necessary, also those containing the component of y. I mean, it's really necessary to test with all subvarieties. Be careful that it is not sufficient in general to test with curves. Okay, I will. This is 2 or 1. Okay. Yes, you just, you can do there is an intersection, I mean, whenever you can intersect two cycles of dimension, codimension n and codimension m and obtain something which is a codimension n plus m. It's just this. So in this case, you are intersecting dim y times with itself, and then you are intersecting with dim y. In this case, there is a well-defined integer number. It's just the intersection function is not defined just for a divisor curve, but you can do it whenever the dimensions are correct. So in this case, it's correct. You can do it. Okay. So, as I said before, we must be careful because it's not sufficient to test with curves. In fact, this will be the content of Climate Criterion. Remark. Having d times c greater than 0 for all curve, does not in general imply that D is ample. We will see an example later. But it does under some additional conditions. For instance, if NE is closed. Kleiman. So if this cone coincides with the closure, so with the Mori cone, then it suffices to have D times C 0 for all curves in order to check ampleness. We will see this later. And then, remark 2, D ample and C any Cartier divisor this implies that D plus TC is ample if T is small enough. So I'm talking of R divisors now. So if you take an ample divisor and you sum to it a sufficiently small multiple of any Cartier divisor, you obtain something ample. Okay, and now there is this famous criterion of ampleness that is called the Climate Criterion. Okay, let me give this statement which contains two pieces of information, X projective variety over C. 1, D Cartier divisor is ample if and only if we have D times X greater than 0, strictly deleted, for all non-zero classes in the Mori cone. Okay, let me give it the second piece of information I will comment. For any ample divisor H and every integer k, the set of classes in the Mori cone such that H times X is at most k is compact. Hence, it contains only finitely many classes of irreducible curves. So let me comment. The first statement here tells us, okay, you want a numerical characterization of ampleness, you have it. A divisor is ample if only if it is, whenever you multiply it by some element in the Mori cone, you obtain a positive number. The elements of the Mori cone are given by combination of curves and limits of them. You also have the limits, because in some instances, the cone NE is not closed. So there are some limit classes that sometimes are not given by effective curves in the manifold. And you must take this into consideration. So we will see an example later due to Mumford, where it is shown that it is not sufficient to verify for X in NE. You really have to check for the limits. And the second part is quite easy because, okay, this is compact. This is not difficult to prove. Then what happens that the reducible curves are discrete inside a compact set. A discrete subset of compact sets are finite. Okay, I will not prove this. You can find it in many textbooks, for instance, in the references I gave, for instance, in Lazarsfeld book or in, I think, also in the Barr book and so on. Just let me give a picture. So assume this is our Mori cone. There can be a polyhedral part. I will discuss about this, maybe some round part here. It can be quite complicated. It is not finitely generated in general. We will see example, but let me give some kind of picture like this way. This is the positive and the negative half spaces. Okay, one says that an E, D is ample if and only if an E minus the 0 lies entirely into the positive half space. So a divisor example, if you take his Mori cone, take the Mori cone of the variety, the closed Mori cone. Sorry. The Mori cone is the closure of the cone of curves. Take this closed cone. It must be, except for the 0, except for the null vector, it must be in the positive half space with respect to the orthogonal. In particular, an E of x is strongly convex. It contains no positive dimensional vector subspaces. In fact, it contains no lines. It is clear because it is completely contained in this positive half space, so it cannot contain a line. Okay. Definition, Neff divisor. A divisor D in X is called Neff, numerically eventually effective, I think. If for every integral subvariety y in X, we have that d to the dim of y times y, the codimension is the right one, so we have an integer number. This must be greater than or equal to 0. In particular, Nakaimo-ish zone ample implies Neff. The converse is false. For instance, if L is a ruling of P1 cross P1, then L is nef, because it moves. So it must intersect. If it moves, so you can move it away from its support. So it intersects positively, not negatively, every divisor. But it is not ample because L square is 0. So by Nakaimo-Ishizon, it cannot be ample. In fact, it is not. Now, we have two associated divisors, again, to ample divisors and to nef divisors, because nef divisors form a cone exercise. Ample classes form a cone that I call amp of x, and nef classes form a cone that I call nef of x. These are two cones inside N1. Well, divisors, so here and here. Very good. Yeah. No. Sorry. Okay, theorem. In N1, we have that the closure of ample cone is the nef cone. Okay, let me close in this way. And conversely, the interior part of the nef cone is the ample cone. So, nef classes are limits of ample classes, and conversely, if you take the cone of nef classes and take the interior part is made exactly by ample classes. Example. The nef cone of P1 cross P1, this is just the closed cone. And this is the closed quadrant, and the ample classes, these are the interior of this, So the interior of this closed quadrant is the open quadrant. In fact, the class of L1 and L2 are not ample. They are nef, but not ample. So the nef cone is the closed quadrant. The ample cone is the open quadrant. And there is something more that we can say, because, OK, there is a duality theorem. And this is important. But let me just start from a definition of duality. OK, take C in V, closed convex cone in a finite dimensional R vector space. OK, the dual cone C star inside B star is defined as, so what is C star? You take the linear functionals here such that when you evaluate them on the cone, give a non-negative result. OK. B-duality tells us that we are in a finite dimensional case. So by B-duality, V double star is naturally identified with V. So under the natural identification, we have that the B-dual cone is identified with C. Theorem. This is Kleiman, if you want. OK. We have two cones. We have the nef cone of divisors. And we have the cone, the Mori cone of curves. And what happens? It happens that nef x is the dual of the dual cone of NE of x, and conversely, by B-duality, conversely. Well, the proof is very simple. You have the intersection pairing. This is a perfect duality. And being a perfect duality, so it yields an isomorphism we are in finite dimensional case. So this yields an isomorphism of N1 of x with natural, if you want. Once you have the duality is natural. N1 of x to N1 of x dual. So that, in such a way, that each functional, linear functional, on n1 of x can be expressed as the intersection product with a fixed class. Uniquely determinate. So, what happens? An fx is okay. Let me start from the other way, which is easier. Okay, this one, what is this? Is phi, the functional, such that phi of x is greater than or equal to 0 for all x in NA of x. But this, for this identification, this is given by d in n1 of x, such that d times x is greater or equal than 0 for all x in NE of x. X is bigger. Okay, and but this by Kleiman. No, this is not Kleiman, this is definition. This is just an F. Okay.
Maybe in the first row,
Yeah?
you have to choose X in
Where?
at the end of the first row.
At the end of the first row. For all x in NE of x.
But this is NE of X.
Yeah, in what I brought. Yeah, sorry. This is just, I confuse things. Okay, so this was missing. Sorry. Oh, now it's okay. Okay, this is just the F. And by B-duality, we obtain nef x dual is an x dual, which is n e of x. Thank you. Okay, I have time for giving 2 examples, or at least one interesting example. For surfaces. Yes, but I mean, nef classes are limit of ample classes. So, yeah, this is definition plus, you are right, plus nef of x is the closure of ample. So the definition of nef is that the intersection is greater or equal than 0 for all element in the yeah. I mean, what I want to this is too much. What I want to say is that if you take it's not this, is plus the fact that let me write in some sloppy way, lim of something which is at least 0, at least greater or equal than 0 is. I mean, if you have some, my definition of nef is that this must be greater than or equal to 0 for all curves, okay, for all effective curves. But then when you go to the limit, this is a limit with non-negative coefficient, so it is again greater than or equal to 0, so it is okay. It is okay. Oh, no. or no? No.
I think
There is some.
it's a separate statement that it's enough to check nearness on curves and not on all varieties.
It is, yeah, okay. Yes, it is sufficient to check nearness for curves. Yeah, this is true. I didn't write this, but this is true. Okay, anyway, this is correct. Maybe there is something sloppy here, but it is okay. Let me give some example. Why every? Okay. Let me give here. Exercise. Okay. X projective surface I'll show that Fx is equal to the Mori cone if and only if C square is non-negative for all irreducible curves. Okay. Now, let me give an example of non-closed NE. Okay. We start from yeah, maybe. I have time for this. Yeah, I have time. Take X, P1 bundle over a smooth curve of genus G. So, in this case, we know that rho of X is 2. So we have this situation here. P1 bundle means this is a smooth curve of genus G, and all the fibers of this map are P1. They are all smooth. Rho of X equal G generated by the class F of a fiber and the class of some section. The existence of a section is not completely trivial. It follows from Sen theorem, for instance, or from some algebraic topology argument involving Poincare duality, as in Beauville book. Anyway, there is a section in this case. Let me call it C0 of some section. A rational section, I mean, which is. So we have this situation here. This is C, and there is this section, C0, and this is F. Okay. So NE of X is a strongly convex cone in P2 So it has two extremal rays. Okay. One of them is always. Okay, now I want to give this example now in order to show that there can be a case in which the cone is not closed, but I need something that I will prove tomorrow. I will state it here. Remark, tomorrow we will see that these curves are actually extremal rays. Now just take it for granted. Allora, one of them is always the class of a fiber. Tomorrow. Let me call this F, tomorrow. F squared equals 0 implies F is on the boundary. Yeah, it's a strongly convex cone. This is on the boundary, so it must be an extremal ray. In R2, because the Picard number is 2 in this case. So it is in the boundary of a convex cone in P2, so it is an extremal ray. Okay. And there is another extremal ray. Let us call Xi the other extremal ray. And consider the self-intersection E minus C0 squared. So there is a distinguished section in this, if you read in the Arshor book, for instance, there is a distinguishing section and with a certain invariant E, which is an invariant of the P1 bundle. And there are two cases to be considered, when this is non-negative and when this is negative. Okay. Case 1, yes, I have time. Case 1, E is non-negative, so this is non-positive. So in this case, again, tomorrow, this spans an extremal ray. And since clearly this is not linearly equivalent to the fiber, this is the missing extremal ray. Very good. So in this case, an E of X is closed. And this is R spanned by C0 and F. Example of this is P1 cross P1. In this case, E equals 0. So P1 cross P1 is a particular example of this instance. Okay, and so we have that. Okay, perfect. So in the C0F plane, we have this situation here. This is closed. In this case. Now we can compute, also if you want in this case, we can compute the Neff cone, which is the dual of this with respect to the intersection product. We can draw a picture by using Neff x equal this one. The duality is taken with respect to intersection product. We can immediately check that. Recall that C0 squared equal minus E, C0F equal 1, and F squared equal 0, because C0 is a section. Neff of x is R So I will write here this other. This is Neff x. And this is a section, again, of self-intersection okay, you have minus C plus 2E plus 0 is E. So in this case, nothing strange happens. The case E at least 0, so the self-intersection of a distinguished section is at most 0. The cone of curves is equal to it's close to the Mori cone. It is given by this quadrant in the C0F plane, and the dual cone is given by this. So the dual cone is the Neff cone. What happened? Something strange can happen. Yeah, maybe I should use the other.
Is there any difference between lowercase f and uppercase f?
Sorry, what?
EF is written in lowercase f?
F, yes. Yeah, it's the same F, yeah. Sorry. You are right, because, yes, of course it's the same F, right? No, this one. No. Why is not going? Because of this. Okay. Thank you. Now, I hope that I can do this. T1 going down, and this one will go down. Yeah, I have 10 minutes to the other case. What happens in the other case? In the other case, something strange can happen. Okay. So, case 2, E is less than 0, C0 squared is greater than 0. So, in this case, one proves that every irreducible curve on X is numerically equivalent either to C0 or to AC0 plus BF with A at least 0 and 2B greater than or equal to AE. Moreover, every divisor such that to B is strictly greater than AE is ample. Hence, some positive multiple is a class of a curve. This implies that one can do the computation. The cone of curve here, the closed cone, is given by this. So in this case, Xi is this. Okay. And one checks also that this cone is self-dual. With respect to intersection product, of course. This is NF. And this is equal to. So in this case, the situation is this. You have F, you have C0, and you have this class here. This is one extremal ray, and the other extremal ray is this. Recall that E is negative now. Okay.
There's a bar missing.
A bar? Where? Here? No. Ah, yeah. Of course. This is the crucial part. yeah, of course. Okay. Important question. Is NE of X closed in this situation? Answer: yes, if the genus of the base is 1. Is at least 1, let's say. No, if the genus of the basis is at most 1. No, if the genus of the basis is at least 2. And this is an example by Mumford. Why? And I finish with this. Well, I mean, no means not always, of course. There are some cases in which it is closed, but there are situations in which it's not closed. And one situation was given by Mumford. There is a following example. Example by Mumford. Okay. For all curves C of genus at least 2, there is a rank 2 vector bundle E, okay, of even degree on C such that all symmetric products are stable. Okay. This implies, with some work, that taking X as the projectification of this E with the natural map over C, no multiple of 2C0 plus AF is effective. In particular, the class 2C0 plus EF is not ample although it has non-negative, it has positive intersection, sorry, with every curve. Okay? Curve on X. So what is the situation here? We have this class, which is an F class, but is not ample. No multiple can be effective. So in this case, this extremal ray given by this class is not in NE. It's in the closure, but not in NE. Note that, by the way, that if you take the self-intersection of this, is 0. It cannot be greater than 0, otherwise my Nakai-Moishe zone, it will be effective, but it will be ample, but it is not ample. Okay. So in this situation, the extremal ray C, which is this, does not belong to an E of X. Namely, an E of X is not closed. So the situation is this. This is an extremal ray belonging to an E, and this F is greater F, of course, and everything. And this is the other extremal ray that does not belong to the Mori cone, to the cone. So in this case, this is an E of X, which is strictly included in an E of X. Just to finish, remark 1. This example shows that in Nakaimo-Ishii, one must check the square greater than 0 of, and also, and not only, dc greater than 0 for c different from d. So the self-intersection is important in Nakaimo-Ishii. You have an example in which the intersection with every curve is greater than 0, but the divisor is not ample. The point is that this condition is not satisfied. D square is 0 in this case. And 2, I finish here. This example also shows that in order to check ampleness, Climate Criterion says that you must go to the boundary, to the Mori cone, to the closure. And this is crucial, because otherwise ampleness can be not satisfied. This example also shows why we use an E of x instead of the closure and not the cone of curves in Climate. In other words, one can say, okay, let me try to find a numerical criterion of ampleness involving this cone instead of the closure. Well, this is doomed to failure because there is an example of this type. I think that this is a good moment to stop. Thank you.